In this video, we shall take a walk through building and fitting a linear model, the complete exercise. So we'll start with the actual setup, construct a linear model, get the data, and understand how the linear model is constructed and how to fit it using R. So we shall start with our familiar example, the spring. Now the moment you get such a system, the first thing that you should always focus your attention on is to get hold of the box diagram, this box diagram. So treat it as a black box, carefully think about what are the inputs and what is the output. Don't forget the random error. I am not writing random error every time. So in this case we have only one input, the weight, and just one output, this length. The input weight is a continuous variable and output is always assumed to be continuous. We have random error. So we expect this L, the output, to be a function of that input weight, the covariate, as well as of the random error. Now once we have this black box, the next thing that you should do is to take multiple copies of this object. In this case it is the spring. Whatever system you are working on, if it is patient, you should take many patients. If spring, take many springs. But make sure that all the springs, all the patients, all the units that you are taking are as identical as possible except for the inputs that you are going to consider. It is true that some amount of variation will be there, they will be considered part of this random error, but try to keep that as low as possible. So if you are working with springs, you now need to procure lots of springs which are as identical as possible. Do not use one steel string and another iron string, one spring which is long and another spring which is short, and things like that. So then you take hold of lots of different such springs and apply different inputs on them. So I have this situation. I have got lots of different springs and I am hanging different weights. So I am giving different inputs to the springs, and the springs are more or less identical. So whatever variability is inevitable comes because of the random error. So I have essentially identical springs. I am hanging some lightweight, so it is short, it is longer, and I am measuring for each of these cases the value of W, the input, and the value of L, the output. So remember, you should take multiple instances of this unit, and if you take n such instances, you are going to get n sets of measurement. In each set of measurement, you will get one value for each of the inputs and one value for the output. In this case, I have a covariate, so continuous input, continuous output. So once you have that, now you should write down the model. The model basically is the mathematical formulation of this black box. So that will look like this. So it is just a way of expressing the output L as a function of the input and the random error. So this is one way of doing it. I have taken L, that output, and expressed this as a linear function of this W plus the error epsilon. That is one way of doing it. So it is L equal to beta 1 plus beta 2 times W plus epsilon. Beta 1, beta 2 are unknown. Epsilon is the error. In our first formulation, we do not put any assumption on epsilon. We are going to put some assumptions later. They are Gaussian or whatever. Now this is for the black box itself. Remember, you have repeated this experiment n times. We showed all those springs. So we have got all those observations. So you must take that into account. So you will write the model now as Li equal to beta 1, then beta 2, Wi epsilon I. Notice that I represents that repeated trials. There is no I in for beta 1, there is no I for beta 2. They are property of the spring. That is why we said that take springs that are as identical as possible. So the idea is this beta 1 and beta 2 is the common property of all the springs. So if they are made up of steel, all of them are made up of steel. If they have initial length, all of them have the same initial length. Try to do it as much as possible. Still there will be some variation which will club inside this epsilon I, and I runs from 1 to n. Now it is time to convert this model to the matrix form, which is pretty trivial. I just write it in this way. So I will write it as all my measurements L1 to Ln equal to, this is what is called the design matrix. Now remember, these weights W1 to Wn are designed by you. So you know what particular weights you have hung from the springs. So you know the exact value, you just know them. There is no randomness in them. So you have this thing, and I have written beta 1, beta 2. So just see that it is beta 1 times 1, beta 2 times W1, etc., plus all the errors. So Ishan asked the question, so how do I get those different errors? Now you understand. I am repeating this experiment every time. For each case, I am getting one line. So since I have repeated it n times, I have got n rows, and I have got two parameters here, two coefficients, beta 1 and beta 2. Hence, I have got two columns. Also observe that the first column of my design matrix is made up of ones. The second column consists of all the Wi's. So that is how you will do this in this particular example. So you got the form y equal to x beta plus epsilon. Here y consists of all these Li's.